Hello everyone, my name is Hao Gao. I'm from Department of Civil Environmental Engineering, NTNU. And I appreciate the opportunity to be with you today. My topic today is the dynamics of ice-lens formation in frozen soil. And I will present you our new model for ice-lens formation using extended finite element method. The outline for my talk today is this. I will start from motivation, concept of our model, to governing equations and the numerical solutions. And then I will give you an example which is solved by our model. Then the last part is the conclusion. As we already know that soil freezing can be associated with some destructive phenomena. We call it frost heave, and it may significant damage our infrastructures like railway or road and our house. And as we can see here, the frost heave is defined as the upward movement of ground surface due to ice-lens formation. And we have already knew that the volume expansion of phase change is not the main reason of frost heave, but ice-lens. So now let's move on to the concept of our model. Here we can see the a set of equations. It's a couple of equations which is from Cygnus non-equilibrium thermodynamic theory. And from this we can know that water flux is not only depend on the pressure gradient, but also depends on temperature gradient, and also the heat flux is not only depends on the temperature gradient, but also depends on the pressure gradient. And there's a key factor here. We call this coupling coefficient, which is from the Nobel Prize winner also gas theory. Okay, let's see the soil freezing process together. When soil is subject to freeze, water tends to the freezing fringe due to the temperature gradient, as we see here. And at the beginning, water can't segregate the soil grains to provide a new volume for transporting. And then pore water pressure will increase as the first term showed, to cancel the water flux caused by temperature gradient. Then it will result in a decrease of effective stress in this part, and at some point the effective stress will be small enough to introduce a crack. From this point, water can freely migrate into this crack and the ice-lens start growing. More penetration of freezing front will result in a dramatic decrease of relative permeability around this ice-lens. Then, consequently, the ice-lens will stop growing, and as the freezing front moving downward continually, at some point, the three requirements, temperature and free enough water, and the mechanical condition for initiating a new ice-lens coincide again. Then another ice-lens will appear and start growing. Then the ice-lens formation circle will be again and again. After this, we can start to look at our governing equations here. There are three governing equations here, and the first one is the Mass-Brownlee equation. As we can see here, the water flux will transfer from the warm side to the cold side, and there are three terms here. The first term is the mass transfer due to the phase change, and the second term is for water flow. And here we can get this QW by this equation, and the last term is for volume change, and we can calculate this delta Vs by using this soil skeleton's volume rate strain rate. Then second one is the energy balance equation. As we can see here, the heat flux will also transfer from the warm side to the cold side. And here there are four terms. First one is for temperature change. Second one is for convection. And third one is for conduction. And here is the conductive heat flux. And the last one is for phase change. And we can obtain the m dot using ice mass balance equation. And the last governing equation is force balance equation. And here is the total stress, which can be composed into the normalized water pressure and the solid phase stress. And this solid phase stress is a combined stress of soil grains and ice. And it's also a part of the total stress responsible for mechanical deformation. So we need a constituted model here. In this stage, we follow an elastic constituted model with a 1D crack criteria f equal to 0. And here A is the ice cementation at fully frozen state. And as we can see here, as the effective stress profile, and effective stress will increase to some point which f equal to 0 and immediately decrease to 0, which means crack happen here. And here we can make a reasonable assumption that crack will appear normal to temperature gradient. And after that, we can start to solve our governing equations. In this numerical solution part, we will have two kinds of REVs in our solution domain. One is without islands and another one is with islands. For REV1, we can use the classical finite element method to model it, but REV2, there are some discontinuities in it, so it's better to use some more advanced method. Here we introduce the extended finite element method, and the key advantage of this XFAM is that we don't need to update the finite element mesh to check the correct path. It extends the classical finite element method by enriching just the solution domain to differential equations by discontinuous function. And there are three primary variables in our equations. They are displacement and the temperature and the pressure. In order to discretize this integral, we need to approximate these three primary variables. Here, the first one is the displacement field. Iceland's growth requires the displacement field to be discontinuous on the interface of islands. So here we use this shift Heaviside function in this enrichment function, and this last two figures is for this enrichment function. And we use this side distance function to distinguish which side of this crack are we in. And it's worth noting that the element will vanish on this not containing discontinuity part, enrichment. And here tells us how to calculate the displacement jump. Then, indeed, the mass transfer and the heat transfer imply that the heat flux and mass flux to be discontinuous on this island's interface, while temperature and pressure field is continuous. So to approximate this, we need to add a continuous function with a discontinuous gradient. Here we use this modified level set function, as we see here. And the last two is for this enrichment function. And also the same as the displacement field part, the enrichment function will vanish as the elements not containing these discontinuities. And here is how to calculate this jump. Then after we carry out this discretization part, we can assemble all these all these equations to a big matrix here, which is an ordinary differential equations in time. Then we can discretize it using fully implicit first order accurate finite difference schema and linearize it. Then we'll get a linear approximation here. And this is residual vectors. And as a result, a sequence of a linear system of equation can be solved to yield a solution satisfying the residual equations within each time step. And this iterative process can last by an appropriate convergence criterion. At this moment, we have finished all our numerical solution part. Here is a one-dimensional example here. This is our model domain. And the cross-section is 1 square meter and length is 0.2 meter. And it has a fixed boundary and dry condition at the bottom and free surface at the top. The temperature here is 2 Celsius degree and the top temperature will vary from 2 to -1. And our aim is to get some result of this model like this ice lens formation. This is the result from our model. As we can see that there are 3 distinct ice lenses from this displacement profile. And also we can see from this temperature and the pore pressure profile, the pressure gradient in these 3 ice lenses changes. But pressure and also temperature at the top and the bottom boundary of this ice lens are the same. And here there's a suction part in this pressure line. And the quantity of this suction has the same order of these experiments. And here is a photograph from table for comparison. And we haven't carried out our own tests, but we will do it later to validate our model. Now to summarize my talk today, here is the conclusion part. Based on the theory of non-equilibrium thermodynamic, a THM model has been proposed to describe the initial and growth of multiple ice lenses in soil freezing. Then temperature gradient is the main driving force of frost-heave phenomenon. The governing equations are solved using the XFAM, in which the ice lenses is treated as a kind of discontinuity inside the corresponding elements. And the last one, the model is applied to simulate a one-dimensional column freezing case. The model works well quantitatively. And that's all my talk today. Thank you for your attention. I will be glad to answer any questions you might have. Thank you.